Hey guys, this is Mr. Backstrom, and today I want to take a look at an example similar to number 27, section 4.9. So we are finally talking about antiderivatives, which is very related to the integral, which is going to be what we're really going to be talking about for the rest of Calculus 1 and for a huge part of the rest of the calculus courses if you're going to take more than just Calculus 1. So very, very important that we understand this and that we learn a lot of the rules of integration, a lot of the tricks, the tools. So let's start with a function. We've already looked at going from position functions down to velocity, down to acceleration. We also need to know how to go the opposite direction. So if we use differentiation to go from position down to velocity, down to acceleration, then we can use anti-derivatives to go the opposite direction. So here they're giving us the velocity, and they want us to go the opposite direction back to the position function. So we can use the antiderivative to do this. We can do this by setting up an integral, and we can break this up into two separate integrals using the sum rule. So what we need to do is we need to know how to find the integral of both a constant, the 5, and an e function here. So let's first start by talking about how we do that. So for an e function, it's going to look like this. If we take the integral of e to some a to some variable, in this case we'll call it a t, that's going to be equal to 1 over that a, e to the at, plus some arbitrary constant c that we usually don't know what it is. Sometimes we do if we're given additional information, like we are in this case here. We can actually figure it out at the end, but often is the case that we just don't know what it is, so we just leave it as a c, or if we have multiple constants, maybe we'll label them C1, C2, C3, but we have to, now why do we have a C? Well, because if we were going the normal direction, right, if we were starting with the position function and we had a constant and we took the derivative, then that constant would go away, right, and we get a 0. So when we're going the opposite direction, we have to assume that maybe there was a constant there. And if we assume that maybe there was a constant there, then we have to put that constant back in. All right, and then how do we find the constant of a derivative? Excuse me, not of a derivative. How do we find the derivative of a constant of just some constant c? Well, that is going to just be, well, let me call it something else. Let's call it a. So we're going to call this, so the antiderivative of some constant a, that's just going to be a times the variable that we're talking about, plus our constant c. So if we're just finding the antiderivative of some constant, then that's just equal to that constant times our variable plus the constancy. All right, so knowing this, we can find this, and then we're going to also use this additional information to solve for the c. So let's go ahead and break this up here. So this is going to be the position function here. So s of t is going to be equal to the antiderivative of e to the negative 2t plus the antiderivative of 5, right? Because we broke it up using the sum rule, and we have these two antiderivatives there. All right, so using what we know, this is going to be, well, that's just going to be, if our a there is negative 2, this is just going to be what? Negative 1/2 e to the negative 2t, e to the negative 2t, plus our constant integration there. So plus, we'll call it C1 since we're going to have a couple of them there. Plus, and now we're going to have our a for this one is going to be 5. So this is going to be plus 5t. And then we'll have another constant there, plus C2. Right? So there it is right there. Now, since, let me go ahead, S of t again. Since both of these are just arbitrary constants at this point, and a constant plus a constant is a constant, I can go ahead and combine them at this point and just into just one constant, right? So that's what I'm going to do here. So this is e to the negative 2t plus 5t plus, and we're just going to say a c here because it's just some constant plus some constant, so that's just going to end up being some constant, right? And now I'm going to use this additional information here and say when our variable t is equal to 0, the function here is equal to 3, and that will let me solve for this constant here. All right, so when I let my variable t equal to 0, so negative 2, we're going to plug a 0 in here, plus 5, 0, plus c, my s's and my 5s look so much alike, I hate that, is equal to 3, right? So negative 2 times 0 is 0. E to the 0 is 1. And 1 times negative 1/2 is negative 1/2. So this is negative 1/2 plus 5 times 0 is 0 plus c. So plus c is equal to 3. Add 1/2 to both sides, and you have c is going to be equal to 3.5 or 7/2. 7/2. So there is our c. So now I can go back to that position function and replace the c with the 7/2. So the position function is equal to negative 1/2 e to the negative 2t plus 5t plus 7/2, and that there is our answer. All right, I'll try to do a few of these because there's a lot of problems in homework 4.9. If you have any questions, let me know, and hope you have a great rest of your week. Thanks.